Nice. Shall share my screen. Hang on a sec. Okay. Hey everyone, welcome to Module 3. This week we're taking an introduction to Solidity. Here we go. So what is Solidity? Solidity is the programming language for Ethereum smart contracts, right? You write code in Solidity and the compiler breaks it down and converts it into bytecode, which is then deployed onto the EVM. Solidity is a statically typed language, which means you have to declare your variable types, and this is then compiled at runtime. Or types are then checked at runtime. It's contract orientated. So why Solidity? Solidity is easy to learn for developers. It's designed specifically for smart contracts, and it has a rich ecosystem of tools and third-party libraries to interact with. The compilation process for Solidity is you compile your contract that's normally into the .sol prefix or suffix, and then the compiler compiles it into bytecode that is then deployed onto the blockchain. So here is a super basic skeleton of a contract. All contracts have a license identifier at the top. This is required by some tooling. It also tells you whether your contract is under a free license or a paid license. Then you have the pragma keyword, and this is just the compiler version for the specific compiler that you want to use to compile your contract. Different compilers sometimes have new ways or new functionality or new things added to them. And if you do not declare your compiler properly, it could use a different compiler to compile the contract and lead to unexpected behavior. That's why when you see pragma solidity caret 0.8.20, this means we're compiling with 0.8.20 or above. This is actually really bad because the caret means that it will compile with any Solidity version that is higher than 0.8, including 0.9, which could have breaking changes. And then here is your actual contract. It starts with a keyword contract and then the name of your contract followed by curly braces. So this here itself is actually a valid contract that could be deployed to the blockchain. Ethereum would happily accept it, but it wouldn't do anything. So the correct way to write a pragma statement is if we go into our VS Code here. You would go SPDX, license identifier, and then your pragma version, you'd have to lock. So pragma solidity 0.8.25. That's my favorite. We're on version 9 at the moment, Solidity version 9. But I like sticking with a few versions behind because they tend to be less buggy. You could also do this, greater than or equals to. So this would lock your pragma to anything that's a minor version. So it would compile with 0.8, 0.25, 0.8.3, 0.8.95, whatever it is, everything up to and excluding 0.9. So it won't compile with Solidity 0.9. But the best way to do it, just lock your pragma like that. And it will compile with 8.25. Then you can have the contract keyword and the contract name. Like that, right? We see. We can do a forward build. And it compiles quite happily. All this is for the other contract that I'm going to show you guys. So here's the structure of a contract. First, we have state variables at the top of your contract declaration, and then functions that do something with your state variables. Here is an example of some state variables. In our contract, it's just a basic counter contract. We've got 3 state variables. These state variables are stored permanently on chain. So these are what we call storage variables. When you write to storage, you pay gas cost to update the storage on chain. Oops. And it's pretty expensive to do. It's the most expensive operation you can do, right? Any storage variable that has a public keyword means it's viewable by anybody on chain. And a public keyword also auto-generates what's called a getter function, which means that you don't have to write a view function in order to look or view at what this variable holds, right? As you can see here, reading these variables are really cheap, but writing them are very expensive, right? Next, we have functions, and this is the behavior of our contract. So for this counter contract, we've got a state variable called UN256 public count, right? And the function, which is the behavior of it, is just called increment. The function keyword declares that it's a function. The name of the function is increment. The parameters go in these surround brackets, and we specify the visibility, which is public. The function body is just what the function does. In this case, it takes the count variable and adds 1 to it. This count plus equal 1 is just shorthand for count is equal to count plus 1. Here you can see what it does under the hood, like we spoke about last week. And that is, let's hide that. And that is, the first thing it does is it loads the count from storage. It then calls the add opcode, which then adds 1 to that count. And then it calls the store opcode, which is the storage write. And then it writes that new number to the count variable. Right? The store is the most expensive of these operations. Okay, there are 4 different visibility rules in Ethereum. So we have public, which means anyone can call this function, both from this contract and from externally outside this contract. It can be a wallet or another contract, it doesn't matter. We have an external visibility. This means that this function can only be called from outside the contract, be it another contract or a wallet. Then we have internal visibility, and this just means that this function can only be called by the contract that the function lives in, or by other contracts that this contract inherits from, or that inherit from this contract. Then we have private, and private is the most strict visibility. It says that only functions inside this contract can call this function. If doesn't matter if you inherit from this contract, you will not be able to call this private function. So I have an example over here in this demo contract. And here we can see we have a few functions. There's a set number function that's public. It can be called by anyone, and its modifier, it's got an access modifier over here. We'll go through that later. We've got the increment function, which is public without an access modifier. This just means anybody can call it. You've got an internal function that just increases the number by 1, right? And then we've got a get function, which is a view function, and an add function, which is a pure function. We'll get to those types later. Both of them are public. because anyone can call them. Okay. If we look at this on our block scanner, which is ETH-Scan, we can see that here's a contract that's being deployed to the testnet. It's got the set number function, the increment function, increment number, and get owner. So if we were to go and look at the read contract tab, we see all our public functions. Here's the get owner function, which is public. It just returns the address of whoever deployed the contract. We have a number function. And like I said, if you have a public state variable over here called number, Ethereum automatically creates a getter function for it. So you can see here, there's the number that returns what's currently stored in that number variable. Currently it's 0 because we haven't interacted with this contract yet. But those are the only functions you see. This user data is a mapping. We'll get to that later. You can see here that the increment function is available, but increment number is not, because this is an internal function. It's only callable by other functions inside this contract. That is the function of internal functions. They are used kind of like this. You can see in this increment function, we do some stuff over here. We set the user ID, the user address, and all of the information. And then we call this increment number function, which is the internal function. And then that just increments the number. That's how we use internal functions in our contracts. Okay, here we can see we've also got a private variable called user ID and an internal variable called owner. Neither of those have a getter function. The user ID function we cannot see in our read variable, the read contract tab. As you can see, there's nothing that returns that. The only reason we can see the owner is because we have a get owner view function, because the state variable is internal. Therefore, we have to write a view function, a specific view function to get it. Okay, moving on. Okay, here we go to view and pure functions. Right? View functions read state from the blockchain only. They cannot modify state at all. Pure functions, they take it one step further, and they cannot read from the blockchain, and they cannot modify state at all. Yeah, I heard a question.
Oh, so I couldn't see the screen.
Oh.
Yes. Now I can see it. So thank you.
You can see it now. Can you see ETH-Scan over here?
Yeah,
Yes,
we can
yes.
see it. Go
Okay,
ahead.
cool. And you can see my VS
Thank
Code. Okay, cool. Okay, cool. So yeah, pure functions, basically they take in parameters and they do something with those parameters and just return the result. So in this case, this calculate sum function just takes a parameter of A and adds one to it. It doesn't read from state. It doesn't read a count variable or anything like that. It doesn't update state. It doesn't write to storage. It just adds two numbers and returns the result. That's a pure function. Both of these functions are free to call if you call them off-chain. So if you call them from your app, from your front end, you don't pay a gas cost to read any of these. If you call a view function or a pure function from another contract on-chain, you pay a tiny bit of gas, but not as much as a normal contract call. Okay, here we've got the most common data types that occur in Solidity. Definitely the most common type is a uint 256 or unsigned integer of size 256 bits. This can store a number between 0 and 2 to the power 256 minus 1. It's a pretty big number, but it's not infinite. And int 256 is a signed integer of 256 bits that can store a number from negative 2 to the power 255 to positive 2 to the power 255 minus 1. Then we have a Boolean, and that's just true or false. We have an address, which is pretty specific to Ethereum, this address type. It's 160 bits, and it always starts with a 0x, and that's the unique identifier for your wallet or your contract on chain. You can think of it as the address to your house or the website domain that you have. It's got to be unique because each wallet that lives on chain is unique to the owner. Then we have a string type, and this is a dynamic type because it can grow or shrink as needed. It's basically stored as a bytes array, and it has to exist in memory when you use the string type. And then lastly, we have the bytes type. This also has to exist in memory. And it's also a dynamic size because it can shrink and grow as you want. So if we look at our contract, our demo contract again, here we can see we've got a few types. We have a public type. We have a uint56. We have an address. We have another uint56 for the user ID. We have a Boolean, and we have a mapping of uint256 to a special type of data called user, right? And this user is a struct. So structs and mappings. Mappings can be thought of as key value pairs, right? In Python, they're called dictionaries, and in Java, they're called hash maps, right? The cool thing about mappings are that they are an instant lookup. So it's got a lookup time of O of 1. So the bad thing about mappings is that you cannot iterate over them. So you can't loop over all the keys in a mapping and say, give me all the keys for this user. They also have default values. So if a user doesn't exist in this mapping, it will still return the user, but all the values will be 0 values, right? As we can see over here, we have a mapping of user ID to the user type, user data, right? And this mapping's name is user data. So if we were to look at the user ID, currently it's set to 1 as here in our constructor. But there is no user data for that user ID because we haven't interacted with this contract yet. So if we look at our read function for user data, for the ID of 1, we query it. We can see the default value for the user address is the 0 address. The default number is 0, and the default activity is false. False just means 0 as well. So we can interact with this, and we can see if it will update. The way we interact with it is we look at our code. We have to call increment, and increment just sets the user as message.sender, as the person that calls the function, sets the number to the current number, and sets active to true. Then it increments the number and emits an event. So if we were to write to this contract, so we can go write contract, connected, and I'm going to make the new number, let's go increment, right? So we have to sign it with our MetaMask, confirm in wallet. Oops. Do that, confirm. And we have to wait a while. It works a bit slow, but when it succeeds, we should see it update. And here we can see this is our transaction details, the transaction hash, the current status of where your transaction is, the block number, the from address, which is my wallet address, the to address, which is a contract. You can see over there, the value that was sent. We didn't send any ETH, the gas fee over here, and the gas price, which is very, very low at the moment. Right, there we can see we have a status of success. So it should have happened. We go back, we go read contract, we refresh, and now we look at user data for user ID 1. Now it's populated. The number is 0, active set to true, and the user address has been set to the caller. The number now is set to 1 because it's been incremented. So as we can see, that's how you interact with the mapping. Structs group related data together. So as you can see here, we have a struct that represents a user object in our contract. This struct stores a user's balance, a user's wallet address, and whether the user is active. If we were to try and store this without a struct, we would need 3 different mappings, one for each user and their balance, one for each user and their wallet, and one for each user and whether they're active or not. And you can see querying this would be a little bit cumbersome. Whereas if you store them all together, you could just call user.balance or user.wallet. You could also store this user object in a mapping with the address of the user as the key to look them up. So they're useful for complex data modeling, and they create custom data types, right? So as we can see here, we've got the user struct. It just has the user's address, the number that was set, and whether it is active or not, right? And this is set in this mapping. It takes the user ID, which is the key, and the user object is the value that relates to. Okay, any questions so far? No? Okay, good. Now we get to events. Events are how smart contracts communicate with your front end of your app or indexes. So it's any way that off-chain systems can get notifications from your smart contracts, right? So whenever anything happens to change state in your smart contract, you have to emit an event so that your front end can stay synced with the blockchain, right? Here we can see we have a deposit function, right? And all it does is it emits the deposit event with whoever called the function and the amount of ETH that was sent, right? Here we have a deposit event, which is defined as deposit, address, indexed user, and the UNT56 amount, right? The amount is message.value, and message.sender is the user's address. The index keyword just tells the front end that this variable is searchable or queryable, and it makes it a lot easier for front-end developers to be able to query or look up this variable. So you can say, show me all the amounts that this user has sent in deposit events. If you want to see more events or the event that we that happened when we made this contract call, you can go to Etherscan. You can see if there were any events that happened. There we see 4 minutes ago, the number change event was emitted with the old number, which was 0, and the new number, which is 1. And there's your transaction hash again, and there's the function signature. We look at our contract. We can see the event is defined up here. and it's emitted every time we call set number and increment. So anytime a number changes, anytime the number variable changes, the number changed event is emitted, so that if we were listening to this from a front end, the front end would know that the number has been changed from old number to new number. If we didn't have events, there would be no way for your front end to know what was happening on chain. Modifiers are, you can think of them as reusable rules for your smart contract. So there was an example in that contract of an only owner modifier. And this basically just restricts whoever can call this function, otherwise known as access control. So modifiers, they help you to reduce the amount of code that is repeated. Because if you had 10 functions that required an only owner check, you would have to write this require message.sender is equal to owner 10 times. Whereas with modifiers, you write this once and you just add the modifier onto the end of the function signature, like this withdraw function. Like we can see here in this function, the set number function has an only owner modifier. That means it can only be called by the person who has deployed this contract or whoever is the owner, whichever owner is set here. All right. The owner is set in the constructor. So when the contract is deployed, whoever calls the deploy function, whoever deploys this contract, is the message.sender, and they immediately get set to the owner. Right. So if any other address attempts to call the set number function, this function will fail. So I can show you that. We go back to EtherScan. We can go read contract. We see who's the owner. The owner is 0x81EF. My MetaMask. Let's cancel this transaction. I'm on account 2. This is 0x73F. So if I go connect wallet, and I don't want to connect with you. Oops. Disconnect. So I want to connect this. Let's just figure out how to connect this. Yeah, it's been a while. Ah, there we go. Connected. So now I'm connected with 0x73, which is this address. It's not the owner of this contract. It's not the deployer. It's not that address. So if I try and write, I connect again. If I try and set a number, let's say make number 5, I say write. It's going to pop up and it will tell me this transaction is likely to fail, right? If I still confirm it, it will fail with this warning, gas limit is too high. But that's not the actual reason that it failed. It actually failed with with the only owner modifier that would say, where's this modifier? Only the owner can call this function. Right? If I disconnect this, I disconnect this, and I connect account 1, who is the owner of the contract.
Where's the power bank?
Inside.
Inside.
On the table. Sorry about that. Okay, now I am connected as the owner. you can see I call set number 5, call write, and it happily goes through. So you can see this is a way to restrict access with modifiers. Modifiers don't always have to restrict access, but it's the most common use case. They can do plenty of other things. Modifiers are written in this specific way, where you have the keyword modifier, then the name of the modifier, normally a required check or some sort of access control or verification, and then this little underscore afterwards. This underscore is just a placeholder for the actual function of the body of the function that should be run. So this little underscore here is all this code over here. So if this require statement passes, it then goes on to this underscore and runs all the rest of the code. If this code fails, it will just revert with this error. Modifiers, as you can see, they're added to the end of your function signatures like this. Right. Here we can see the hierarchy of your function visibility modifiers. So public is at the top, anyone can call it. External means only outside of your contract. Internal means this contract and all contracts that inherit from it. And private means only this contract. So if you put it all together, here we have a simple bank contract that has an address, public owner. It has a mapping that stores a user's address to a UINT256, which represents their balance. So you can call any user's address as the key, and it will tell you what balance or how much ETH they've deposited into this contract. We have a deposit event with a user and amount parameters. We've also got the only owner modifier. Got a constructor. The constructor is a special type of function. It only runs once when you deploy the contract. And it's pretty useful for setting up initial state of your contract. Then we have the actual deposit function over here. And it's got the special keyword called payable. This payable keyword just means that it can receive ETH, which is the native currency of the network. Here you can see we've updated the balances for the caller of this function. So we call this balances mapping, and we just add the value of ETH to whatever it was before. Then we emit the deposit event with the caller of the function and how much value they have deposited. This bank function is missing a withdraw function, but that withdraw function would be pretty similar to this. It would just have a modifier that would check that the user has a balance, a positive balance, and that the amount that they are trying to withdraw is not greater than the balance that they have available or 0. So we have some security considerations when writing smart contracts. We've always got to use access control. So use your modifiers to protect your functions and always check message.sender when needed. Message.sender is just the caller of the contract or the caller of the function. It can be another contract or it can be an external wallet. So if you really want to be safe, you always have to check who is calling your contract and if that person or contract is allowed to be calling it. You should also be careful with storage rights, because storage rights are the most expensive operation you can do on chain. If you have incorrect storage, it can lead to a corruption of state, and this can be really, really bad for your users. You have to always emit events whenever you update state, because this is how your front end stays in sync with the blockchain. And finally, we have to watch for reentrancy with any external function calls. Reentrancy is probably one of the most common attacks that we have in smart contract development. And just think whenever you have an external function call, you can be called by another contract while your function is still executing, and this can have unexpected behavior. So we'll cover this more in detail in our security module, but for now, it's just good to know what it is. Okay, so recapping, Solidity is the language for Ethereum contracts. State variables are stored permanently in storage on-chain. Functions define the behavior of our contract. View functions don't modify state, and they're free to call off-chain. Mappings are key value lookup tables. Structs group related data together. Events emit logs for off-chain systems. And modifiers enforce reusable rules. And storage rights are the most expensive thing you can do on-chain. That's why when you develop smart contracts, you always have to think about gas and always how you can minimize storage rights. Okay, that's it for now. Any questions? Did I go a bit fast? Was it too slow? Was it boring?
It was cool. It was
Yep.
entertaining. I should have brought popcorn. No,
yeah.
I'm joking, man. It was good. It was good.
My favorite thing about Ethereum or any public blockchain is the block scanner. It just provides that level of transparency that's missing in any other centralized application. Where else can you go and actually read the code of the contracts that you interact with? You can actually see if you can read code, you can actually see exactly what the contracts are doing and what it's gonna do with your money. And then you can also play around with it if it's on testnet. You can interact directly with contracts on mainnet if you know how, via a block scanner. You don't have to go via a front end. So I think these things are pretty cool and pretty nice to monkey about with. Like you could literally punch in any address that you know of and see if it's a contract. You can see how much ETH balance it holds. You can see you created it. So for instance, if I punch in this address, which is this wallet address, and I say go. There we go. It shows me my ETH balance is 0.418 blah, 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 0.418 Sepolia ETH, right? The last transaction was 8 minutes ago. The first one was 2 hours ago, right? There's all the transaction logs for this contract. You can see whoever interacted with it. You can see which functions were called. You can see when it was called. You can see who called it. You can see the amount of ETH that was sent with it. If you dig in deeper in transaction hash, you can see the status. You can see all the information about it. If you go into more details, there you can see events. You can see the gas fees that we used. So these block scanners are incredibly useful for debugging, especially, but just to give yourself the confidence that what you are interacting with is indeed it's not trying to scam you or not trying to be malicious in any way. So you can prove this for yourself, which is the beauty of Ethereum, if you ask me. So yeah, that's my lesson for tonight. If anyone has anything to add, please feel free. Would you like something more practical? I can give you some homework.
I think
Yes,
that will be
please.
cool.
Yeah. Cool. So if you guys want to write your first basic contract, I will push this to a repo, to the ETH-Course repo. There's this my contract over here, it's blank. You guys can totally write something based on this demo, as well as the slides, and then push it to your repo, or push it to your personal repo and share it. Share the
Just
link.
make a branch.
Yep, and we'll have a look, and we can play around with it the next time.
Cool. Now I've got a question for Mr. Vickers. Like, what do you recommend? Like, how do we vibe it? Or should we just build it normally?
You can totally vibe it.
I think for the essence of learning, you should do it manually by hand.
Okay, fair enough. No, because like there was open Zeppelins that we looked at like a while ago, and like a whole bunch of other stuff. And I'd rather be crazy and do something like bananas, dude. Like,
Yeah, no,
I guess a
no,
banking
so-
app is cool. So yeah.
I understand, but if you don't understand the fundamentals, then when
Yeah.
you
But
start
dude-
vibing,
How else are you supposed to create someone that can get hacked? We're disempowering the hackers here by writing secure code. Come on, guys. No, I get you. So definitely, I'll do it the manual way.
you have to learn how to crawl before you can run.
Fair enough. But yeah, well, how about like we didn't do the withdrawal side, so I think that'll be interesting to do. But it's the
Yeah.
same thing, kind of. So yeah.
No, that's good. Or if you want, I could add the deposit side to this contract, and you guys can finish the withdrawal function if you want.
Yeah, that sounds cool.
Yep.
Yeah.
Okay, awesome.
With some
Uh,
brain power, like yeah. What else do they have? There's withdrawal, there's overdraft. Okay, I'll figure out my own crazy stuff. But I think like
Yeah.
looking at like all the banking things would actually be good for the brain. So,
Cool. And then we can go through it, and we can have a look at it in next week's class before we start. Someone can share the screen and take us through it.
sounds good. Very cool. Like I'm looking forward to next week's session. Thank you, Mr. Miles. Appreciate you.
Cool.
Thanks everyone for joining. I'm gonna kill the session now. If that's cool.
Yeah, cool.
Buttons to push, dude. Buttons to push.